time, Newton's first law is, if there is no force on a particle, the particle stays at rest or it moves with a constant velocity. So, in varieties of ways you can state the same thing, but essentially that is the first law, that if the force on a particle is 0, if the force on a particle is 0, then the acceleration is 0. Then the acceleration of the particle is 0. Essentially is this in a nutshell, because if it is at rest and remains at rest, that means acceleration is 0, or it moves with a constant velocity in the same direction, same speed, that also means acceleration 0. So, if you are talking of a particle, if the total force on the particle is 0, then the acceleration should be 0, and vice versa also. This, if acceleration is 0, right, if acceleration of a particle is 0, then according to Newton's first law, you can always say that the net force acting on the particle is 0. So, both ways, both ways. So, that is Newton's first law. Let us first talk of this, Newton's first law. No force, no acceleration, that is Newton's first law. But that is not always true, that is not always true. If I am in a rotating frame, or let us say I am in a car, accelerating car. So, if I am in an accelerating car, right, it is accelerating and I am sitting here, somewhere here on the seat, okay. So, I am sitting here, and then from the car's body some pendulum is hanging, right, some pendulum is hanging. What I see? I see that the pendulum, the string does not stay vertical, it makes some angle theta with the vertical, all right. Now, if I think of this particle, this bob of the simple pendulum, what are the forces? The forces are its weight mg and then the tension T. These are the two forces, because force is always exerted by some object, right. Force is by some object on some other object, that is how the force is conceived. So, the earth which is attracting everything, so it is also attracting the bob, and that force is mg in the vertically downward direction. And then other than the earth, the only thing in contact is this string, and string always exerts force along its length, string always pulls, and therefore, the force on this bob by the string is in this particular direction along the string. There is no other object which exerts force on this, and these two forces are not equal and opposite, and they will not add to 0. So, you have a net force, force is not 0, but what I see? I see that it is at rest and it remains at rest, okay. So, the acceleration is 0 for this observer here. If he puts the origin here, x, y, z axis, no coordinate is changing with time, x coordinate does not change in time, y coordinate does not change in time, z coordinate does not change in time. So, it is at rest, it remains at rest, acceleration is 0. So, force is not 0, but acceleration is 0. So, that means this this rule that if force is 0, then the acceleration is 0, and if the force is not 0, then the acceleration is not 0, that rule does not hold here. And if you have a resultant of these two, and if you want to make force 0 and apply a force here, you apply a force here, you pull it, you hold the bob and pull it. Why? I want to make the force 0. this tension here, this mg here is giving me some resultant, and I apply a force to make this force, total force 0. What will happen? What will happen? This bob will be accelerated towards me. If I pull it, the bob will be accelerated towards me. So, F is 0, but A is not 0. Newton's first law is not valid in this frame, or if I am in some kind of a rotating frame, I am on some disk, and there on the disk I have put my x, y, z axis, then also this does not hold. So, Newton's first law is not a universal law as such, because we are always free to choose our frames of reference. Whatever is suitable for me, I will use that frame of reference. So, for some frames of reference it holds, for some frames of reference it does not. So, essentially what this Newton's first law is doing, it is defining or it is classifying that okay, there are at least some frames in which this holds, and we call them inertial frames of reference. We generally live on the earth, whatever we do, our activities generally because the technology is advancing very fast, and we are going to in spacecrafts to other places, moon and Mars and all those things, but most of the time we are on the earth, and therefore a very suitable frame of reference is earth, and that is not inertial, that is not inertial. Now, no one can compel me that no, do not use the lab frame, do not put your x, y, z axis in the lab, and you have to go for an inertial frame, first search it, put your x, y, z axis there, and then do all the physics, all the mechanics, all the dynamics. That is not the way science goes. So, I am always free to choose my frame of reference, and if it suits me, I can use this frame or some other frame, whatever I like. So, this Newton's first law is essentially, it defines. Fortunately, the earth's frame of reference is close to inertial, although it is non-inertial, but it is very close to inertial. If you think of this condition that if f is 0, what will happen? The acceleration will be very small, exceedingly small. So, we can take it as inertial frame of reference, and if the acceleration of some object is 0, how much is the force? In the frame of earth, if I am there, how much is the force? How much the force needed to make the acceleration 0? That force is exceedingly small, and therefore we generally take earth as an inertial frame of reference, but whenever we want to do some physics where the accuracy is important and our instruments are sensitive enough to detect small changes in the motion, or we can measure very small forces, then yes, we do take care of the fact that earth is not inertial. So, this first law actually defines inertial frames of reference. And once the inertial frame of reference is defined from here, then we go to the second law. In an inertial frame, force on a particle, net force on a particle is equal to mass of the particle into acceleration of the particle. So, many times people say that okay, why first law? From the second law put A equal to 0 here, F will be 0, and that is the first law. So, first law can be derived from the second law. That is not very true, because this is also valid in an inertial frame, but what is inertial frame? That comes from the first law. So, first law has its own independent significance, and once the inertial frame is checked from here, then we say that okay, in that inertial frame this will happen, and that is our Newton's second law. And then we have Newton's third law, which is very different from all this. It is called laws of motion. First law, second law, third law, these are called Newton's laws of motions, but the third law does not involve motion as such. So, if I talk of third law, okay, and that says that force by particle 1 on particle 2 and force by particle 2 on particle 1 at any instant are equal in magnitude and opposite in direction. I have written a long statement of Newton's third law. Force by particle 1 on particle 2 and force by particle 2 on particle 1 at any instant are equal in magnitude and opposite in direction. Whereas the most popular version of Newton's third law is that action and reaction are equal in and opposite. But that short, the crisp, very simple, beautiful statement of Newton's third law, every action has an equal and opposite reaction, has caused lot of confusion in the interpretation of Newton's third law, lot of confusions. So, basically the content of Newton's third law is, if you have two objects and they are exerting forces on each other, remember, for any force you can ask these questions: which object has exerted this force, on which object this force is exerted, okay? What is the magnitude, what is the direction, but basically from where the force is coming. So, which object is exerting the force and on which object it is being exerted. So, that is very, very important. So, if you have two objects, one is exerting force on the other is also exerting force on the first one. So, that is it, force by particle 1 on particle 2 and force by particle 2 on particle at any instant. This is also very, very important. In an action reaction statement, it appears that first some force was exerted, which is action, and then reaction also occurred. So, it is in reaction to the first force, the second force is exerted. It is not that, it is at any instant, at one single instant this is exerting force on that, at the same instant this is exerting force on this one. So, which one is action and which one is reaction has no significance, absolutely no significance, because at any instant, at one particular instant, this object is exerting force on this and this object is exerting force on that, and the two are equal in magnitude and opposite in direction. So, that is Newton's third law. The motion is not involved as such here, but how the forces are related. Here also there is yet another thing which we can add here in the Newton's third law, that and are these forces along the line joining the particles this also you can add. If you have a particle here A, if you have a particle here B, the force by A on B and force by B on A at any given instant are equal in magnitude, opposite in direction, but that could have been this way. That could have been this way. The directions are opposite, the magnitudes are equal. So, this statement is satisfied. But the other part which you can add is that no, the force is along, these forces are along the line joining these two particles. Okay. Now, if that does not happen, maybe in some cases if it does not happen, then this part will not be valid. Now, if you stop here, what is Newton's law? Force by particle 1 on particle 2 and force by particle 2 on particle 1 at any instant are equal in magnitude and opposite in direction. This, if you stop here, this is sometimes called weak form of Newton's third law, right. This is sometimes called weak form of Newton's third law. And when you add this also, that the two forces are along the line joining the particles, this is sometimes called strong force, strong form of Newton's third law. Okay, so we will stop here and we will talk further on forces in the next lecture.